All right, everyone. Mr. Graham here. Today we're gonna expand on some ideas concerning Gauss's law. Just as a quick reminder, let's talk about what we figured out yesterday. If we have a point charge, we can surround that point charge with a Gaussian surface. We do so that the electric field on the entire surface. This is a two-dimensional surface in a three-dimensional space, so it is a spherical shell, essentially an imaginary one, surrounding our charge positive Q. These are positive charges. If you have negative charges, everything's the same, just in reverse. We surround with the Gaussian surface. We use Gauss's law for electric fields to determine this equation here. What we already knew, the electric field is just kq over r squared. But when we use Gauss's law, we see where that k comes from. It's actually 1 over 4 pi epsilon naught. And so the electric field here is going to be 1 over 4 pi epsilon naught times the charge q divided by r squared. I like to think of this as this is a vector equation. Remember, Gauss's law involves a dot product, so the result is a scalar. E dot dA is a scalar. That tells us the flux density, essentially, how many electric field lines are passing through the surface. The charge is either positive or negative, the charge enclosed. And so if it's a negative charge, you have negative flux, which tells us then that the electric field lines, which are vectors, point into the surface. If Q is positive, then the electric flux is determined to be positive using Gauss's law, which tells us that the electric field lines point away. So the electric field is a vector field, in fact. And so we can actually say, well, this electric field, if we're interested in the electric field just along the x-axis, I can say this is this quantity times I hat. That tells us the electric field at that particular location. Now, if I'm not on the x-axis, if I say I want to find the electric field at this location, well, then I use this distance, but I don't use x, I use r. And then I would just multiply it times the unit vector r hat. And that just tells us that's the general form of that equation. So in general, it's going to be times r hat, and r hat just points in the direction of the electric field. We also want to think of, if I have larger Gaussian surfaces, that means I'm farther away from the charge, and we know that the electric field is inversely proportional to the square of the distance. It's an inverse square law. So what that tells us is that the electric field is actually a function of the distance from the charge, the distance r. And so I could say that the electric field is a function of r. And then I could plot the electric field versus r. In this case, it's x. So in this particular situation, we're just going along the x-axis, but in general, it is r, the distance r, the position r, I should say. And so if I was to plot the electric field here as a function of distance, well, right on the charge, by this equation, we have an infinitely large electric field. And so we have an asymptote right here whenever x is 0. But we all know what the shape of y equals 1 over x squared, what the shape of that graph looks like. It looks like y equals 1 over x, but it just hugs the axes a little tighter. And so if I was to plot the electric field versus position here, then I would get this graph. That's what the electric field versus position for a point charge would look like. That's what we expect, hopefully. What if we have a charged insulating sphere? Not a point charge, but an actual charge that has some physical dimension. So not a proton, not an electron, but an actual charge, say a plastic sphere or a bowling ball type sphere that we charge uniformly throughout its volume. Then, well, what happens, how do we deal with this situation? Because yesterday we just talked about point charges. Well, Gauss's law makes this pretty much the same situation as this one, because I'm going to do the same thing. I'm going to draw my Gaussian surface such that I have the symmetry here where the electric field is going to be the same over the entire surface. So I'll make it three-dimensional. So I have this Gaussian sphere. Notice the charge enclosed is still the total charge. So using Gauss's law, which again, let me reiterate, the Gauss law says the closed integral over the Gaussian surface of all the dot products of E and dA, all the electric fields dotted with dAs, I add all those up over that closed surface, I get the enclosed charge divided by epsilon naught, like we talked about yesterday. But remember that we want to draw our Gaussian surface so that this integral is actually easy. If we don't have a nice symmetric Gaussian surface, we can still do it. At least not now, though. You'll have to wait until you do multivariable calculus in college. That's why in this class we use nice symmetric Gaussian surfaces. So Gauss's law tells us that if I draw my surface like this, the electric field is constant over the entire surface. And then notice that the enclosed charge is just the total charge, just like it is here. So I end up getting the same result. The electric field at this point outside of the sphere, as a function of radial distance, and actually let's not talk about the function now. We'll dig into that in a second. The electric field at this point here, we'll call that point P. The electric field at point P, if we run through the Gauss's law like we did yesterday, if we run through Gauss's law, then we get that the electric field at this point is simply the same thing, because we'll have the same amount of charge enclosed. So our result will be identical to this. It'll be 1 over 4 pi epsilon naught times the enclosed charge, which is just positive q, divided by the distance from the center of q to that point squared. And again, if this is, it is technically, in general, r times r hat, but in this case, it's on the x-axis, so we can just say times I hat. Right, so this is the magnitude. I hat gives us the direction. That tells us the electric field vector at point P. And I can plot this as well. However, I need to be a little more careful because I don't have electric field. Let me redraw those axes, sorry. Let's say, so the electric field as a function, and since we're on the x-axis, let's just plot it on the x-axis. But the thing is that starting at the surface, so I'm going to note that on my graph here, this is capital R, where capital R will be the radius of my Gaussian surface. So if I find the center of my Gaussian surface, that's my radius. Outside, I'm sorry, not the radius of the Gaussian surface, my bad. That's the radius of the actual charged insulating sphere. Okay. So up until that radius, there's some different physics going on, which we'll talk about in a second. But outside of that radius, we have an identical equation. It works exactly the same way. And so if I was to plot this, I would actually have the electric field strength starting here. And it wouldn't be at infinity because essentially it's going to be infinitely large at the center of the sphere. But once I get to the outside radius, that's where I can start treating it like a point charge. And at that distance, I'm at a radius of capital R. And so this equation right here will become, the electric field strength will be, hopefully you can see why this is true, 1 over 4 pi epsilon naught times the charge enclosed, which is the total charge, divided by the distance, but in this case, it will be the radius of the actual sphere squared. And so that's going to be the strength of the electric field on the outside, an infinitesimally small distance above or outside of the the surface of the spherical charge. Okay. And so up until we get to R, we have electric fields on the inside, which are going to be a little more complicated. We'll deal with that in a second. But once we get to R, that's where our electric field strength will be. And then it will fall off according to the inverse square law. So it will look like this, only that's not going to start happening until we get out to the radius of our Gaussian sphere. So what goes on in here? That's what we're going to talk about now. And we can use Gauss's law to deal with this as well. This is just going to be a slightly more complicated version of Gauss's law, or a slightly more complicated application of Gauss's law. So let's take our charged insulating sphere. And I'm going to draw it large because we're going to, in order to determine the electric field inside of the sphere, so that we can write an equation that will tell us the electric field as we go from the center of the sphere to the outside, so we can fill in the rest of this graph. I'm going to draw it larger. We're going to have to draw our Gaussian surface inside of the sphere. Okay. So I have an insulating sphere. Again, this is a three-dimensional object. We have charged uniformly. We have this object charged uniformly throughout its volume. It is an insulating sphere, so the charges aren't free to move. And so I'm going to indicate that by just drawing a bunch of positive charges. And again, this isn't two-dimensional. These positive charges are evenly distributed throughout the volume of our charged insulator. Okay. I'm going to put it like I did over here on our axes so that I can figure out a way to actually plot the electric field. So X and Y axes. And let's say I want to determine the electric field at this point within the charged sphere. Well, let's use Gauss's law. Let's draw a Gaussian surface inside there. Again, we want to draw a Gaussian surface so the electric field will be constant over the entire surface. The only way to do that is to have our Gaussian sphere concentric with the actual spherical charge distribution. So that'll look something like this. So here's my Gaussian sphere in green. And the radius of that Gaussian sphere, obviously it will change as we go from 0 to the radius of the actual sphere. I'm just going to call that radius r. Now I'm going to use Gauss's law in order to determine that electric field, the electric field at this point here. You might guess that the electric field is going to point outward from the sphere, and you'd be right. But to show why that is the case, let's actually just do the problem. So we're going to use Gauss's law, which says that the closed surface integral of E dot dA is equal to the enclosed charge divided by epsilon naught. Now it's kind of interesting because as long as we have the symmetry, the left side of this equation is generally, in more complicated situations like this, the left side of the equation is generally easier to deal with. The crazy looking integral thing, it's easier to do. The hard part here, it's not that hard, but you have to use a different skill. The harder part here is determining what the enclosed charge is. Let's say we know the total charge on the sphere is positive q. Well, the enclosed charge is not positive q because I have charge outside of that Gaussian surface. So to deal with that, we're going to go back to charge density. We can use our charge density knowledge in order to determine what this enclosed charge is as it relates to the total charge. Right? We want to relate the charge inside of this sphere to the total charge. And to do that, we can deal with the charge density. Volumetric charge density, this is a volume. So volumetric charge density is rho, and that is just charge per unit volume. The volume of our insulating sphere is 4/3 pi times the radius of the sphere, capital R, right? The radius of our sphere here is capital R, cubed, right? That's the volume of that. If I have uniform charge density, though, this should be exactly equal to the enclosed charge divided by the volume of the Gaussian surface. Charge density inside our Gaussian surface should be the same as the charge density of our actual sphere. So that'll be over 4/3 pi times little r cubed. Right? Well, here, obviously, 4/3 cancels, pi cancels, and now I can determine the enclosed charge, determine an expression for the enclosed charge in terms of the total charge Q, the dimensions of the insulating sphere with its radius, capital R, and the distance from the center within the sphere that we're dealing with. And so I can write that my enclosed charge here would then be, I just multiply both sides by RQ, and I get that it's essentially the ratio. It's Q times the ratio of the cube of the distance from the center to the radius of the charge itself. All right. So that's our enclosed charge. We're going to have to plug that in for the enclosed charge here, and then work Gauss's law to determine this electric field. And when I do that, I'm going to go ahead and start Gauss's law again. Just write the equation again. Get used to writing this. The integral, closed surface integral of E dot dA equals the enclosed charge divided by epsilon naught. I've drawn my Gaussian surface so that actually before I do that, I'm going to note that the dot product of E and dA gives me the scalar electric field times dA times the cosine of the angle. Well, if I've drawn my Gaussian sphere symmetrically, then the electric field and the area vector, the infinitesimally small area vector dA, will point in the same direction, which tells me that the angle between them is 0, so the cosine of the angle is 1. So E dot dA just ends up being E dA. So I can substitute that in our integral. So I have the closed surface integral of E times dA, again times cosine theta, but cosine theta is just 1. That's going to equal the enclosed charge divided by epsilon naught. The electric field is constant, so it can come out of the integral. So I have the electric field times the closed surface integral of all the dAs. That's going to equal, well, my enclosed charge is Q, total charge, times the ratio of the radii. The ratio of the Gaussian surface radii to the Gaussian surface radius to the radius of the insulating sphere itself. And when I do that, I will get Q times r cubed, little r cubed, over big R cubed times epsilon naught. So I've just substituted this in for my enclosed charge, and I get that. Well, now let's do this integral. Well, if I add up all the area vectors for the Gaussian surface, it's literally just, like, I don't have to do any fancy math here. I just have to say, well, this closed surface integral of this Gaussian surface area is just the total area of the surface, which is 4 pi times little r squared, right? And again, that's going to equal Q times r cubed over big R cubed times epsilon naught. Remember, little r is the radius of the Gaussian sphere. Big R is the radius of the charged insulating sphere. Now, if you notice here, r squareds cancel with 2 of those r's, and I divide both sides by 4 pi, and so I get that the electric field, the strength of the electric field will be 1 over 4 pi epsilon naught, otherwise known as Coulomb's constant K, times, now what do I have left over? I have Q times R over R cubed. The result is positive. The result is positive, which tells me that the electric field, the field lines are flowing, or the flux is pointing, or it's flowing out of our Gaussian surface, which means at this point in the x direction, it is in the positive x direction. So I can say that this electric field is pointing in the I hat direction. How would I plot this, though? If this was, remember, what varies here as we go from the center to the radius of the insulating sphere, what's varying is r, little r. That's the distance from the center of the charge to the point that we're interested when it comes to the electric field. Well, that means that if I was to write this as a function of r, my electric field as a function of distance from the center, little r, is going to be equal to 1 over 4 pi epsilon naught, again, otherwise known as Coulomb's constant, times Q over radius of the insulating sphere cubed times little r. And then again times I hat to make it a vector equation. So this is our result here. Well, what type of equation is this? How would I plot this on this graph here? Well, the electric field inside of the charged insulating sphere is linearly proportional to the distance from the center, which means at r equals 0, we actually have a 0 electric field. And then as r increases, the electric field increases proportionally. And so it's a linear proportion. So for an actual charged insulating sphere, we start with an electric field of 0, and it climbs linearly until we get to this point, where our electric field at the surface, right at the surface, is given by this equation, right? 1 over 4 pi epsilon naught times Q over big R squared. That's this equation, but evaluated at the actual radius of the insulating sphere. And then it falls off according to the inverse square law. Okay, so that's how you deal with electric fields inside of a charged insulating sphere. And I'm going to stop it here and come back in another video because I'll probably mess up and I don't want to make these videos too long.